Hello everyone. We have done some of the applications of Ampere-Circuital law. The first application that we discussed was to find the magnetic field at a point due to a straight current carrying wire. In the second application, we have calculated the magnetic field at different positions due to a solid cylinder. Third, we have done it for hollow cylinder. And now in this video we are going to discuss and derive a relation for the magnetic field at a point due to a coaxial cable. By the coaxial cable we mean, let me give you an example first. The cable which is used to connect your dish antenna to your set-top box of the TV. That wire is actually a coaxial cable. If you cut through it, you will find that there is a inner wire or the inner cylinder which is covered by an insulating material, and there is an outer cylinder also which is hollow. So here we are going to consider a coaxial cable, and because of which we are going to find the magnetic field at different points. So let us see how it is done. It is an application of Ampere-Circuital law only. We will be using the Ampere-Circuital law. Let me show you first the cross-sectional area of such a coaxial cable. This is the top view of the cross-sectional area. That means if we are considering a coaxial cable like this, so this portion we see from this side, so this is the top view of the cross-sectional area which is shown in the diagram. Now as I told you, in the diagram you have the inner cylinder which is solid cylinder of radius R1. Then there is a space for insulating medium. Then there is an outer hollow cylinder which has an inner radius of R2 and the outer radius of R3. So this portion represents the outer hollow cylinder. So here, for an example, the insulating material which we are considering is air. Air is in between the two cylinders. And always remember one thing, whenever current flows through coaxial cylinder or coaxial cable, the direction of current is opposite. Like when we consider the inner cylinder, if the current is in the outward direction, then for the outer cylinder having a thickness of R3 minus R2, this cylinder will have a direction opposite to it, that is in the inward direction. So in this situation we have 4 points where we are going to find the magnetic field. First of all, the first point is inside the inner cylinder. Second point is in the insulating material, that is air which we are considering, which is the gap between the inner and the outer cylinder. The third point will be inside the inner cylinder, the outer cylinder, and the fourth point will be outside the coaxial cable. So these are the 4 points that we are going to consider one by one. So let us see how it can be done. The first condition that we are considering here is when the point is inside the inner cylinder. That means we are considering a point inside the inner cylinder which has a radius of R1. Now if a point is considered in the inner cylinder, as we have done in the earlier video, we have discussed it, we will consider the point, that means the Amperian loop will be in the form of a circle, and the radius of the Amperian loop given by small r will be less than R1. Okay, so small r is less than R1. So naturally, if I is the total current which is threading through the whole cylinder of radius R1, which is the inner cylinder, so from the Amperian loop it will be lesser than I. The value of that I can be calculated. So let us see how it is done. We are using the Ampere-Circuital law, which is integration B dot dl over a closed surface is equal to mu naught times the total current threading the Amperian loop. Now the current per unit area, I is the total current through the inner cylinder, per unit area, that is pi R1 square, into the area of the Amperian loop will give you the current which passes through the Amperian loop. So the area of the Amperian loop is multiplied, which is pi R square. And the next step we see integration B dot dl. We have earlier discussed in the videos that B and dl, they are parallel to each other. So B dl cos 0 is 1. So B comes out, integration dl. And integration dl will be the circumference of the circular Amperian loop, which is 2 pi r. And here we have the values. And if we solve it, you can see here many terms will cancel out. If we want to cancel some of the terms, small r cancel out, here the square term will cancel out, this pi will cancel out, and this pi will cancel out. So now we can have the value of B, which is the magnetic field, which will be given by mu naught by 2 pi IR by R1 square. So I hope this is very clear to you. So inside the inner cylinder, the value of magnetic field is directly proportional to R. R is the distance from the center. So let us now move to the next portion, that is the insulating section. This is when the point is in air in between the inner and the outer cylinder. Okay, so we are considering the point in between R1 and R2. This portion, you can see the portion to be a little gray in color. So in this portion we are considering the point. So the value of Amperian loop, that R1, which is the radius of the inner cylinder, is less than R, and which is less than R2. So now again using the Amperian loop, integration B dot dl over the closed loop is equal to mu naught into the total current threading the loop. Now the total current threading the loop is exactly the current which passes through the inner cylinder, which is given by I. So integration B dot dl, it is B dl. As we know, angle is 0 degree. So integration dl is 2 pi r, and we solve it. The value of B comes out to be mu naught by 2 pi I upon r. Here you can see in this region, in air, the value of magnetic field is inversely proportional to r. We are considering this. You remember these points because we are going to draw the draw a graph between B and R. Okay. Now next position, we are moving to the next position, that is when the point is inside the outer hollow cylinder. Okay, that is when the point is inside the outer cylinder, when the value of R will be in between R2 and R3. Like this is the inner radius of the outer cylinder, R2, and this is the outer radius of the outer cylinder, which is given by R3. So the value of R, which is the distance from the center to that particular point now which we are considering, will be greater than R2 but less than R3. Now one more thing you need to understand, when we will be using the Ampere circuital law, integration B dot dl is equal to mu naught into the total current threading this loop. Now this is the loop which we are considering here. Now in this loop we need to understand the current which threads the loop. Now there are two sets of current. One is the current I in the inner cylinder, and another is the current here in this portion. In this portion which is left out here, in this portion we have the value of current in the opposite direction, right? The current I is here in the outward, so here in this portion the current will be in the inward direction, so it will be subtracted from the value of the current I, because this portion of current is moving in the inward direction and this is the current which is in the outward direction. So the outward direction we have the value of current which is given by I minus the current which belongs to this region. not in the whole cylinder, whole outer cylinder, but only up to this portion, because this is the Amperian loop which we are considering. So this portion current we need to subtract. So first of all, we will calculate the current per unit area of this outer cylinder. Now the cross-sectional area of the outer cylinder is pi into R3 square minus R2 square. These are the radius square, outer radius and inner radius we are taking. I hope you will understand this. So this value gives us the current per unit area of the outer hollow cylinder. Now we need to find the current within this region, which is in between R2 and R. R is the radius of the Amperian loop. So the cross-sectional area of this portion, which I am showing you here, this portion cross-sectional area will be pi R square minus R2 square. So this is the cross-sectional area. So when we multiply current per unit area into the area inside the Amperian loop, which belongs to the outer cylinder, so we get the current, the whole current, which has to be subtracted from I. And so we have the value here, integration B dot dl, we again solve it, and we have B into 2 pi r, the angle here is 0 degree. And in this part also we solve it, and we have the relation here. And finally the value of B here is given by this formula, mu naught I R3 square minus R square divided by R3 square minus R2 square into 2 pi r. Here also you see that the magnetic field B is inversely proportional to R. Go through this portion very clearly. If you don't understand is one time repeat the video, you will surely understand. Any doubts, I am there. Move to the next point, that is the fourth point which we are going to consider, and it is the point which is totally outside the cable, coaxial cable. So we are considering the point here which has a value of R. The radius of the Amperian loop now will be greater than the outer radius of the coaxial cable, which is R3. Now we will use the Ampere circuital law, which is integration B dot dl over a closed surface is equal to mu naught into the total current threading the loop. Now the currents are in the opposite direction. In the inner one it is I, but in the outward direction. In the outer hollow cylinder it is in the inward direction. So they will cancel out. So the net current is 0. So integration B dot dl will be B into 2 pi r. The value of magnetic field will be 0. That is, outside the coaxial cable the magnetic field is 0. I hope this is clear, the 4 points. Now let us see the graph between the magnetic field and the distance from the center. You can see here when R is less than R1, that is inside the inner cylinder, that is the inner wire, you can consider the magnetic field B is directly proportional to R. In between, that is in air, that is in between R1 and R2, it is inversely proportional to R. Between R2 to R3, that is in the outer cylinder, it is also inversely proportional to R, and beyond R3 it is 0. And the values at the peaks here at R1, that is at the surface of the inner radius and at the surface of the outer radius, these are the constant values which are shown here in the figure. So I hope this is very clear to you. Any doubts, you can post me the doubts. Thank you.